Good afternoon, everyone. My name is Gavin McCullough. I'm a system development engineer in Amazon Route 53. I've been in Amazon for about 10 years, and I originally joined to work in Amazon's load balancing and DNS teams, the teams that actually owned Amazon's own and AWS's own DNS and load balancing. But in more recent years, my focus has been on Route 53 Public DNS, Route 53 Resolver, and most recently, Route 53 Application Recovery Controller. With me today is Jeff Damick, who's a lead software development engineer on the Route 53 Resolver product. For those of you not familiar, Route 53 is the name for Amazon's suite of domain name system or DNS products. We provide a pretty wide set of capabilities at this point, including domain registration, hosting zones, and health checking to help with failovers, as well as Route 53 Resolver for use within EC2 and hybrid networks. In August of this year, we also launched Route 53 Application Recovery Controller, which I'll explain a little more toward the end of this hour. So the idea of this talk is we aim to catch you up on all the new features and capabilities we've added in the last year to 18 months. So hopefully you should come away with a more up-to-date feel for what's possible using Route 53. As Jeff is the lead engineer on the Resolver team, he's going to start off explaining some of the new features in the Resolver product, including IPv6 support, improvements to forwarding rules, and query logging. After that, I'm going to talk a little about Route 53's new DNSSEC capabilities, and finally about Application Recovery Controller, or ARC for short. So I'll hand over to Jeff now to get started.
Thanks, Gavin. As Gavin mentioned, I'm going to tell you a little bit about some of the features that Route 53 Resolver has launched over the last year and a half. But before I do that, I want to take a quick second to review what Route 53 Resolver is. So you may have heard it called by different names. So in the DHCP options for your VPC, you may see it referred to Amazon provided DNS, or in other documentation, you may see it called the VPC plus 2 Resolver. All of that is Route 53 Resolver. And Route 53 Resolver provides recursive DNS service to any of the resources you have in your VPC. So for example, your EC2 instances, your Lambdas, these sorts of things. And a few years ago, we launched inbound and outbound Resolver endpoints. And so what those provide are ingress and egress of DNS queries to Route 53 Resolver. So inbound endpoints allow you to send DNS queries from on-premises over Direct Connect or VPN to Route 53 Resolver. And likewise, the outbound endpoint allows you to send DNS queries, direct them from your Route 53 Resolver back to on-premise. Maybe you have a DNS server running there and you want to send some of the queries back to that DNS server. And Route 53 Resolver also provides the DNS recursion out to public DNS authorities and other outbound endpoints and private hosted zones. So the first feature I want to talk about is related to reverse records. So you may have an Active Directory server running on premises and you want to direct reverse record queries, PTR queries, back to that Active Directory server. So these are typically the reverse of the DNS queries that you would think of normally. So normally people think of DNS queries as getting an IP address for a name. In this case, you're getting a name for an IP address. And so previously, you would have the situation where you would have to create forwarding rules for all of the CIDR blocks related to your VPC. And if you look in the diagram, you can see as you add more VPCs, more CIDR blocks, and add more CIDR blocks to your VPC and peerings, it can become unwieldy and hard to maintain all of these different forwarding rules. So what we've done is we've added a toggle. So now you can disable this default behavior in Route 53 Resolver. So normally, Route 53 Resolver will auto-define these forwarding rules for you. And they will be resolved by Route 53 Resolver. But now you can turn this off and you can direct those queries back to on-premises, back to your Active Directory server. So if you just create a dot rule and disable the auto-defined reverse record rules, all of those queries will be directed back on premises. And another feature we released recently is related to IPv6. So in your environment, if you have an IPv6 dual stack and you're migrating to IPv6, you can now access Route 53 resolver over an IPv6 address. The IPv4 address is still there. It's the 169.254, 169.253 address. But now, on Nitro instances, you can access a native IPv6 address to access Route 53 resolver. And another feature we launched a little over a year ago is Resolver query logging. So Resolver query logging has a few different use cases. So you can use it for compliance. You can gather Resolver query logs and run auditing on it and determine if there are threats. Maybe you can use it for threat detection and identify issues running in your VPC. You can use it to debug and see how instances are querying and what they're querying within your VPC. So going back to the architecture diagram I showed previously for Route 53 resolver, we can see where query logging fits into the picture. So you can see that all of the queries that are going to the public authorities and other points now are also being fed. Those query logs are being fed to Resolver query logging. And then out of Resolver query logging, you can decide where you want to send those query logs to be analyzed. You can send them to Amazon CloudWatch, Amazon Kinesis Data Firehose, or Amazon S3. And then run analytics and possibly hook into third parties software from there. So let's see a sample of Resolver query logs. So this is the JSON example of a query that I performed in my VPC. You can see it has the query type, the response code, the result code, the answers, and also importantly, it has the instance that made that query. And so if you hook Resolver query logs into CloudWatch Contributor Insights, you can gather even more information about what's going on inside your VPC. And Contributor Insights has some sample queries already defined that you can take and add those rules to Contributor Insights and immediately start getting some analytics and determining what you see inside your VPC. You can track your query types, result codes, and more. And we'll see how that works in a minute. But first, let's walk through setting up a query log. So in this case, I've created Resolver query logs, and I'm directing them to CloudWatch, and I've set up my CloudWatch destination here. And next, I'm going to go ahead and add my VPC that I'm going to collect Resolver query logs for, and I'll go ahead and configure it. And so once I've configured my query logs, they'll start capturing those queries. So you can see it's activated. Now it's going to activate on that VPC. And once it's active, then the query logs will start flowing to the destination you've determined. So in this case, I've created a CloudWatch logs endpoint for it. So let's see what happens when you query. So in this case, I'm going to dig Amazon.com from an instance inside my VPC. You can see the answer that comes back here. But now let's look in CloudWatch. So in CloudWatch, we can see that the query log is added, and you can see the same information. The answers are also in the query logs, as well as the result code. And you can see the instance ID that performed the query, the account, the VPC, and a lot of information, metadata about it. And let's also look at a negative example. So in this case, I'm querying test.amazonaws.com. And this doesn't exist, so it's going to return an NX domain to me. And you can also see that in the Resolver query logs as well. So you can see that the result code is NX domain, and you can see which instance performed that query. So going back to that NX domain, so it may be interesting for you to look at how many instances are receiving NX domains, what the top queries are. So how do you do that? So you've created this, you create the contributor insight rules, and then you can take those rules and put them into a dashboard. And then this is where it's very powerful. You can see what's going on inside your VPC. You can see how many, what are the top domains being queried within your VPC, for example. You can also see what the top result codes are. So if you see a lot of NX domains or serve fails, you may want to determine what the instance is that's making those, or or that sort of thing, and see where they're coming from, what the cause is. And in this case, I determined that the serve fails were all coming from failuremodes.damic.com, which is a test domain that I created that's returning serve fails for me in this case. So that's the highest contributor to serve fails right now. Another feature we launched about a year ago is DNS Firewall. And so DNS Firewall provides protection from exfiltration, for example, so you can prevent people from exfiltrating data over the DNS protocol to malicious sites. So you can block those sites, you can block access to those. You can also block malware, botnets, and other these sorts of things. And so you can even go as far as creating a walled garden and really only allow certain sites that you want your resources within your VPC to be able to resolve. And so some of the DNS firewall features are, like I mentioned, you can have deny lists, allow lists, and then you can decide the action that you want to take based on the match for that domain name. And we'll get into that in a second. And we have malware and botnet pre-generated lists that you can choose from, and you can also get the visibility of the instances within your VPC that are making these queries and how it's being determined and blocked. So going back to our architecture diagram, we can see where DNS Firewall fits into the resolver picture. So we can see that all the queries coming out of the resolver are all passing through the DNS Firewall before they recurse out to private hosted zones or public authorities. And at a high level DNS Firewall, you create firewall groups. And within the groups, you create rules and domain lists, and you decide the action that you want the firewall to take. And then you associate those to your VPC. And you can manage those also with AWS Firewall Manager and manage those across multiple accounts. And using Firewall with Amazon GuardDuty and Amazon Detective gives you more rich analytics and information if you want to identify the root cause for particular issues or suspicious activity, and then you can take action and block those sites within DNS Firewall. So let's walk through an example of setting up a DNS firewall. So I'm going to create a demo firewall group, rule group, and then once I've created that rule group, I'm going to add a rule to the rule group, and in this case, it's matching example.com. And so for example.com, the action that I'm going to take is block. And we're going to return an NX domain in this case, instead of the normal IP address that example.com would return. We'll add that rule to our rule group. Click Next. And now we have that rule within our rule group. And we'll go ahead and create the rule group. Once it's created, then you can see that it's created, but it's not associated to any VPCs yet. So now you need to go in, you can view details, and you can see that there's no VPC associations yet. So here we're going to choose to associate it to a VPC. Once it's associated to that VPC, the policies that you've created, those rule groups, are enforced on that VPC. But let's go ahead and let's say we want to redirect a CNAME. So you want to create a captive site for your users, and you want to redirect them to a different CNAME. So in this case, I'm going to match on cname.damic.com, and we're going to return a different address to those queries. And I'm going to return local.damic.com, and this is just an example here that will return a different IP address to those querying that. So we'll go ahead and add that rule to the rule group. And so let's see what happens when we query. So querying from an instance within our VPC, we're going to dig for example.com, and we see it returns an NX domain as we've decided. But let's look at our resolver query logs and see what information we have. So now within our resolver query logs, along with the instance that made the query and the result code that came back, you can also see the firewall information. So you can see the firewall group that matched and the domain list that particularly matched that query, and then the action that the firewall decided to take based on those. And now let's look at our CNAME example. So we're going to dig to the resolver inbound endpoint in this case, and we're going to dig for the cname.damic.com, and we can see that it returned local.damic.com, and then the CNAME was chased, and it returned 127.0.0.1 as the IP address. And now when we look in resolver query logs, we can see that along with the other query information, we see that the source IDs are the resolver inbound endpoint IDs. So you can track the resolver inbound endpoints that are receiving these queries as well as instances. And you can also see the same firewall information, so you can see the action that was taken and the matches that determined how that action needed to be taken from the firewall. So we'll go back to our Contributor Insights dashboard, and there are also sample Contributor Insight rules for DNS Firewall that you can add. So I've added those to my existing dashboard, and you can see in this case, now I have blocked queries, and I can see the top contributors that are blocked within my VPC. You can see that it's example.com and cname.damic.com. And let's say you're interested in finding out which endpoints are being blocked the most. You can create a dashboard for the blocked sources, and you can see which resolver inbound endpoints are receiving the most queries that are being blocked. So perhaps you have something sending queries from on-premises, and a lot of those queries are being blocked. You could track it here and dig further into it to determine where those queries were originating. And with that, I'm going to hand it back over to Gavin to take you through the Route 53 DNSSEC.
Thanks, Jeff. So let's talk now about Route 53's DNSSEC product. We launched this in December of last year. And if you're new to DNSSEC, which a lot of people are, that's okay. I'm going to explain it here from the basics. So first of all, what is DNSSEC and what problem does it actually solve? So DNS was designed in the 1980s, and back at that stage, security wasn't really the top priority. People were really getting things working with the internet. And so more recently, people have focused more on making DNS more secure. And so DNSSEC is the DNS security extensions. And so what does it actually do? Well, the idea is that when you're making a query against a DNS resolver, in the original DNS implementation, there isn't really a way for the resolver to authenticate or to ensure that the answers it's getting are authentic. And so when you're connecting to web services, ideally you want your resolver to be able to make sure those answers are authentic. And so that is the problem we're solving here. And if you are running a web service for your customers, you want them to be able to make sure that the answers your DNS is giving are authentic. And this will become a little bit more clear when I show you a picture. The most common reason people want to do this in practice is for compliance reasons, and particularly the US government and a couple of others have compliance requirements that require DNSSEC or something very similar to be used. And an important thing to understand is that this is about ensuring that the answers are authentic. We're not actually encrypting the traffic in transit here. So the problem we're solving here is making sure that you get the right answers, not necessarily encrypting things. So let's dive in a little more detail. What exactly is DNSSEC? And I'm going to start off here with the model that Jeff showed us before. So you have, maybe you're using the Route 53 resolver, and the queries, you send queries to the resolver, and it can query private DNS or the VPC DNS. Those are secure and over the AWS network, so we don't worry too much about them. But the other option is, a lot of the time, it will need to query public DNS authorities, and that can be over the internet. So that's the case that we're most worried about. So let's adjust our picture a little bit. We have the client querying the Route 53 resolver, and the Route 53 resolver on the client's behalf querying public DNS authorities over the internet. And actually, it doesn't really matter what resolver we're talking about. This applies with any resolver. They all query public DNS authorities over the internet in practice. So let's look at what that actually looks like, querying the public authorities. This may be something that's very familiar to you, but I just want to run through it because it makes it easier to understand how we add DNSSEC later. So a client will make a query to a DNS resolver, and the DNS resolver will walk down the DNS tree from the root through COM, and in this example, gavinmc.com's name servers. So you'll see, in response to that query, the resolver will make a query to the roots, to the COMs, COM name servers, and to the gavinmc.com name servers. And now the resolver will have the answer and respond back to the client. So let's zoom in a little bit more on exactly what we're seeing there. So again, client queries the resolver, resolver queries the root server. What comes back? So it's a query for www.gavinmc.com, and the response is what we call a referral, which is to say the root servers are saying, we've delegated COM to these other name servers, so you should go and talk to them for anything called COM, anything that is something.com. And so the resolver then makes a query to the COM name servers. And they get back another referral to say, well, the COM name servers, we're delegating authority for gavinmc.com to these 4 name servers that happen to be on Route 53. And so the resolver gets that answer and makes another query to those gavinmc.com name servers. And now, finally, we get an answer. And it's 3 IP addresses. Great. And now the resolver can respond back to the client. So this is how the recursive DNS resolution process works. And so just recapping, this was designed a long time ago, and it was designed to be unencrypted and without any way to authenticate the answers. So if you were hypothetically somewhere on the internet, or if there's somebody in the path of these queries, they'll be able to read them on the wire. It's not necessarily a massive concern, but it is a thing. And so DNSSEC, it's important to understand, doesn't actually change this. The queries are still readable on the wire. However, before DNSSEC, they were also unauthenticated, meaning that the resolver couldn't actually tell if the answer was authentic, if it was really talking to the right party at the other end. And if you imagine someone on the wire, they might actually be able to forge an answer back to you. So this is the issue that DNSSEC is there to address. It adds cryptographic signatures to the responses in order that the resolver can tell if these answers are authentic or not. So let's look back at our model. We have the client queries the resolver, and all of these queries between the resolver and the authorities are unencrypted but also not authenticated. And with DNSSEC, we're going to add in signatures on the right-hand paths in order that the resolver can see if the answers are authentic. So how do the resolvers actually verify the answers are correct? So the authorities, the right-hand side name servers, they start signing answers that they return to the resolvers. So every DNS zone will have, and in the picture we had the root zone, we had the COM zone, and we had a gavinmc.com. They will all each have a cryptographic key pair. And they will return to anybody who wants the public key in a new record type called DNS key. I'll show you the actual type in a minute. And then at every delegation point where a name server is referring you to another name server, they will pass you an extra record called a delegation signer. And basically what that is saying is, when you go to that name server that I've pointed you at, you should expect their DNS key to have this fingerprint. And you can trust them if the key has this fingerprint. So that's what the DS record is for. And then finally, once you're talking to a zone and you have a key established that you can trust, they will sign all the answers they give you with an ORORSIG record that you can use the key to validate. And so the resolvers use this combination of establishing the key for each zone and then looking at the signatures of every answer to establish what is called a chain of trust. So let's look back at our model again quickly, and we'll add in DNSSEC. So the query again goes to the clients, and we query the root. So this was the response we had before. This time we're going to see something new. An extra record is here. So this is a referral to the COM name servers. And we're getting this extra record, which is the DS, or the delegation signer, which says, when you go to the COM name servers, These are their addresses, but when you get there, their DNS key should have this fingerprint, and you can trust them that they are the right people if they have that fingerprint. And then in order that you can trust me, you already know my key, so here is a signature that you can validate that that this DS record is trustworthy from me. Okay, so then we make that next query to the com name server. And this is a new query. We're going to query for the DNS key of the com name server. And we get a response back. It has its own signature. And we can use the DS we got at the previous step from the roots to tell that this DNS key is the right, that we're getting answers from the right people. And now we make the usual query. We get back a referral to gavinmc.com. And we get a DS record here too. So this is to say, this is the com name server saying, when you talk to the gavinmc.com name servers, this is their key. This is what it should look like. And I'm going to sign it so that you can trust my response for the DS. So now we start making queries to this gavinmc.com name server. Again, we query the key first, and we compare it to the DS record we got from the com name servers. And finally, we make the query we had before, so we get our answer back, and we get a signature along with it. And this allows us to trust this signature because we've established the chain of trust down through all of the name servers. We know what the key is for gavinmc.com, and we can check that this signature matches that key. Okay, so in doing this, I'll talk a little more about Route 53's DNSSEC. So when we were designing this, we went through some kind of design tenets. One of the important things was that we wanted to make this as simple and safe and easy to use as possible for customers. So, for example, we didn't want customers to have to create signatures themselves. So the signing is all automatic. And the key management is all automatic as well. Every zone that you use with DNSSEC with Route 53 will need a key, and that is automatically managed for you. The other thing that we thought about was making sure that absolutely every other feature would just work. So when you turn on DNSSEC, everything else just works as normal. There's no kind of like trade-off there. And so now I'm going to walk you through 3 of the kind of most obvious normal DNSSEC tasks with Route 53. The first one being enabling DNSSEC validation in your VPC. So if you use the Route 53 resolver in a VPC or in a hybrid network, you send queries to our resolver and you want us to validate those queries when querying authorities online. So you can go to the Route 53 console. It's very simple, and you can go into the VPCs, and you'll see here that there's a VPC listed, and over on the right-hand side, the DNSSEC validation is disabled. So we click on the VPC, and we can go in here into DNSSEC validation and enable DNSSEC validation on this VPC. And that's really it. That's done. And obviously, you can disable it in the same way. So the next task that we'll go through is, let's suppose you're providing a web service online and you want to sign your zone in order that your customers can validate DNSSEC. So the first thing we do is enable signing on the zone. And then the next thing, and that has no effect directly, and then when we insert the delegation signer at the parent zone, that is when DNSSEC comes into force. So let's first enable the DNSSEC signing on the zone. So we go into the Route 53 console and we can see my hosted zone here. There's a tab for DNSSEC signing, and you can see that it is not signing currently as the status. So I click on Enable DNSSEC signing, and now we're going to need to create a key. And Route 53 will walk us through this very easily. So we create a name for the key. I'm going to choose to create a new key, though I could reuse an old one or a common one for multiple zones if I wanted. And we're just going to create KSK. And that's pretty much it. And this pretty quickly after that, the signing status will change to signing. And so now what's happening is we are returning signatures along with queries. And if I was to look in the KMS console, when we created a key in your account for in the key management service. So you can see that key is there. So what did we actually do in terms of our kind of model of queries? When we make those queries now, or when a resolver makes queries to gavinmc.com, it will now be able to query the DNS key for the first time. That record set will now respond. And if the resolver makes queries asking for signatures, it will get them. This zone is now being signed. And so that's the change that we've made there. Now, an important step here is to actually wait for a while. There may be DNS resolvers which have cached records from within the zone which are unsigned. And so you want to wait for a little bit of time in order that those entries can be flushed and that signed entries will start to appear before we do the next step. So the next step is to place the DS record at that parent zone, at the COM zone. And that is the point when we're telling the world, you should expect signatures from the gavinmc.com zone. So going back to this console, how do we do this? You can see view information to create DS record. And then we can click into that and we can see 3 fields: the type, the algorithm, and the public key. If you don't happen to be using the Route 53 registrar, there are some other fields that other registrars will use. They're all displayed there if you need them. So I'm going to use the Route 53 registrar or Route 53 domains. And you can see here, I go back into my domain registration, and we can see DNSSEC status is disabled. So I click on that, and I put in those 3 fields: the type, the algorithm, and the key. And press add, and I'm done. And now you can see DNSSEC status over on the right here is enabled, and we can see the key type. Okay, so what did we do there? In the model, the query now that goes to the COM DNS server, when we get that referral, COM is going to respond with this extra DS record. And that is the signal to all DNS resolvers that they should expect signatures from the gavinmc.com zone. We've already established the signatures in advance, but now the world will start to expect them. Okay. So the last thing, and that is pretty much complete once you've done that. And the last thing that I'm going to explain is how you disable that, because it's a little bit of a sensitive process and I want to make sure that everybody understands how to do it. So the order in which you do this is the reverse order of what we did when enabling. So the first thing we have to do is tell the world to stop expecting signatures. So we go back into the domain registrar, and we go in and manage our keys, and we're going to delete the key here. And this is removing the DS record from the COM zone. And now that information will have been cached for typically up to a day, maybe even a little longer. So after doing that, you need to wait for 2 days. You need to keep signing responses until everybody has realized that the DS record is gone. And now we can go back into the Route 53 console for the zone itself, and we can click on Disable DNSSEC signing. And then you're done. So the next question that we get a lot from customers is, should I enable DNSSEC on my zone? Is this important? And the answer kind of varies a little bit. DNSSEC is still something of a niche feature, and so you need to think carefully about it. If you want to learn and experiment with DNSSEC, absolutely, you should just go ahead and do it. If you have a public zone of your own, I would definitely do it. And if you need it for compliance reasons, that is one of the main reasons that we built DNSSEC into Route 53. So absolutely, yes, this is the thing to do. If you're running a production website and you don't have a specific requirement for DNSSEC, I guess we would say that you need to think carefully about the trade-offs. So there's a level of extra complexity being added to your DNS when you enable DNSSEC. And so there's a bit of a trade-off there between, I guess, security and complexity. And so that's just something you need to think about carefully. One other thing I would mention is that you need to keep track of always be aware of the caching implications. So I've put in those previous steps a couple of wait times. Those are really important to keep in mind, that resolvers don't necessarily see what you do immediately after you do it. It may be some hours or even days before they see it. Okay, so if you're enabling DNSSEC, let's talk about some best practices. The first thing is that, as I mentioned, we put the key Route 53 will create the key for you in your account. And that's in order that you have control of it, which is important. But one of the downsides of that control is that, maybe you have a new colleague who disables a key, doesn't understand what it's for, or something like that. And the effect of that will be that we will have to stop signing at some point if you were to revoke Route 53's access from a key or delete the key. So we publish a metric in CloudWatch for this in order that you can see. Essentially, it's a signing error metric. And it will be 0 all the time, or should be 0 all the time. So if you're using DNSSEC on a production important zone, I would set an alarm on that CloudWatch metric, and that will allow you to get, if for some reason somebody was to delete the key or revoke Route 53's access to it, you will get a warning early that shows you that you need to undo that before there's any problem. There is a process for rotating the key signing key, which involves taking multiple steps, including going back and updating the DS record. It's a fairly intricate process. We describe it here in this blog. I guess the main thing is, if you need to do that, I would practice it on a non-production domain first. It is still a fairly complicated process because it involves multiple parties. And finally, if you're migrating onto Route 53 or from Route 53 to another provider, you almost certainly want to disable DNSSEC while doing that. And go through the process that I mentioned earlier on, taking the time and the wait time during it. Okay, so the other part of this talk is about Route 53 Application Recovery Controller. So let's dive in there a little bit. So in talking to customers, we've come across a few what we would term almost extremely reliable needs of customers to create extremely reliable applications. And so we're talking here about potentially less than 5 minutes of interruption per year, which is really quite hard to do. And in some other cases, we've had customers who need to be able to tolerate major extreme events like a natural disaster. And this is where Application Recovery Controller comes in. So if we're talking about the number of failure minutes per year, there's essentially two fields two parameters that matter here. One is how often failures happen, and the other is how long they last when they occur. And the formal way to put this is the mean time between failures multiplied by the mean time to recovery or repair from failures. And so essentially, if you're trying to make your service more reliable, you've kind of two options. One of them is to make failures less regular, and the other is to recover faster from them when they happen. And this is kind of an area of academic research called recovery-oriented computing. If you build very highly reliable services, if you're in that game, I would recommend reading this paper. It's from 20 years ago, but it really has stood the test of time, and it's been very influential on Amazon and AWS. And the idea that's put forward here is there's only so far you can go with making failure less and less likely. And you actually have to focus more or as much on how quickly you will recover from the failure. And so you need to build into your design a plan for how you recover quickly when things fail, because it's going to happen. So two of the key system design ideas that they brought in were that you should compose your system from multiple redundant isolated units. If you're familiar with RAID technology in disk storage, it will feel familiar, the idea of having multiple copies of or multiple replicas of a system, and the ability, if one of them fails, to tolerate by just leaning on the others. The other is to have tested recovery mechanisms, so when one of these failures occurs, you need to have a way to take the failing unit out and continue with the other remaining units. So ensuring you can recover from an event. The first thing we do, as I say, is we're going to build redundant replicas, multiple copies of the application. And we're going to ensure that all of the replicas are always ready. In an active-active situation, this might mean that they're always ready to take the extra load if one of the replicas fails. In an active standby, it typically involves making sure the standby is a perfect replica of the primary in order that it can take over without a hitch. And then the other thing we need to do is now that we've created multiple replicas, we need to minimize the shared fate between them. There's no point in building an active and a standby if both of them fail at the same time. So you really need to think carefully about when you're deploying only one at a time, and when you're making any kind of modifications, only one at a time, and having them on completely independent infrastructure so that they don't fail at the same point. And so when one replica fails, you need a mechanism to remove the bad replica and lean on the other replicas. So a couple of examples here to make this a bit more concrete. We've talked before about the Route 53 resolver, and this is kind of the architecture we're talking about. And there's a core component in there, the resolver, the big square in the middle. And so your instances are making queries against that resolver, and we're forwarding them to various other parties. So in practice, what we found worked better was to actually say, well, that single resolver, we have a single unit there, and we're going to need to make changes. It's not one host, it's a fleet, but we're going to need to make changes there, configuration changes. We're going to need to do deployments, and they all sit on some infrastructure. So what we found worked better was to say, we need full redundancy here. We actually need 2 fleets. So that we can tolerate the failure of one of those fleets. So, and these days that is how. It isn't even 2 replicas anymore, there are multiple replicas, but we have multiple replica fleets like this. And the idea here is that if A1 were to fail, all of your queries are going to A2 as well, and we will just smoothly keep going. So probably something that's slightly more close to home for you is building a 3 availability zone web service. So we're in AWS, we're going to build across multiple availability zones, and these are going to be our replicas. We're going to have a small fleet of instances in each availability zone. We're going to have a single database because regardless of which, our customers are going to make a write of some sort, we're going to, and regardless of which zone they go to, they want to see that write immediately. So there's a kind of a core database that's shared between the 3. It might be in either of these availability zones, but it's common to all 3. We put load balancers in front of the instances to scale and be able to take an individual host out quickly. And then we use a Route 53 hosted zone, which will have the name of the service. So our users will make a quick DNS lookup, and that will direct them to one or more of the NLBs. Okay, so we have our multiple replica setup now. The idea is that either zone A, B, or C can fail, and we will just take it out and the other 2 zones will work. And this is an active setup. All 3 zones are active all the time. Now, what recovery mechanisms, the question that arises, what recovery mechanism would we use for availability zone B failing? And one way is to go into the Route 53 hosted zone and remove it. Route 53's API is a control plane. And so it's pretty highly available, but maybe we can do better. Another question is, how do we make sure only one AZ is removed at a time? People who build a 3 replica system probably will only build enough capacity to withstand the loss of 1 zone. So we wouldn't ever want to allow the system to drop down from 3 to 1 because we're probably out of capacity. Another pattern that we see with some customers I mentioned before is people who need to prove they can recover from major natural disasters. And so they need to move the application to a completely different part of the country to recover. So a typical pattern, very similar to the last one, we're built out in US East 1, we have a couple of replicas, and we have a hosted zone, and our users connect through that. And now the question is, if we had a major disaster on the East Coast, what would we do? So we build a standby in US West 2. And this is a standby that is replicating from US East 1, but it is not active all of the time because when a user makes a write, they want to be able to see the write immediately. And so it's important for consistency to keep only one region active at a time. And so this is an active standby setup. And again, the questions that arise: what recovery mechanism do we use during a failover? And how do we know the standby is ready for production? How do we make sure one region only is ever in production? It's important in an active standby that we would never promote both and have both in service at the same time, because that would cause consistency problems. So this is the area in which Route 53 Application Recovery Controller is, or this is the kinds of problems that it is designed to solve. So we have our multiple replicas. How do we know we're able to take a replica out? How do we know we're ready? What recovery mechanism are we going to use? Because it's probably a big disaster happening and we need something that's going to be reliable. And how do we make sure the failover is always safe? So let's go into the first question. So Application Recovery Controller provides readiness checks for this. And so if we look at our active standby situation, essentially what we're trying to do here is to say, we have this primary region, we know it's taking the traffic. The standby copy of the service is essentially, we need to make sure it is a perfect match for the primary. And over time, as the service grows, we're probably going to scale up the primary region. We're going to make various changes to it. And so what readiness checks are there to do is to constantly compare the standby region to the primary and set off alarms for you if for some reason the standby isn't up to date with the primary. And so you have a safety mechanisms that stops you from scaling up the primary region and forgetting to do the standby. And so this is what readiness checks are for. And so looking back at our model here, for example, we have an auto-scaling group in each of those active AZs. And so what readiness checks will do is make sure that the parameters on the auto-scaling group match in US West 2 in order that when someday we need US West 2 to take over, it will be ready and scaled. We can also get readiness checks for the NLBs to make sure, so you potentially have provisioned capacity on the NLBs, and we'll want the same provisioned capacity in US West 2. We have an Aurora database in this case that is replicating cross-region, and again, we'll need to make sure that all of the parameters are the same, the instances are the same size, so that it will smoothly take over. And finally, we can set up Amazon CloudWatch alarms. If the templated readiness checks aren't quite what we want, we can create CloudWatch alarms in each region and have readiness checks monitor those. Okay, so the second question we had was, what recovery mechanism do we use when we do need to do this failover? And so we have this setup, and we need to be able to quickly shift from US East 1 to US West 2 with high reliability. And for this, Application Recovery Controller offers routing controls. This is a highly available API to directly control failover. So the API is spread across 5 regional endpoints in 5 different regions in order to be extremely tolerant of even big failures. It also orders all of the changes strictly in order that if 2 changes were to come in quick succession, perhaps take AZ-A out and another one take AZ-B out, we can be careful about not breaking safety rules. And so let me show you this with a specific example. Essentially what you end up with is a highly available API that looks like these buttons. So right now, the buttons are saying East 1 and West 2 are both good. And because we have it set up with East 1 as the active, that's what's going to happen. Now, if East 1 were to fail for some reason and we need to fail over, we will use that highly available API to flip that button, and that will control a health check in the Route 53 hosted zone, which will cause all the users to shift over. So DNS will change highly reliably, and US West 2 will take over. Now, the last question we had was, how do we make sure failover is safe? So safety rules within the ARC routing controls are for this purpose. So you can set up a set of preconditions for any change when you're making a routing control change. So as an example, one of the things you might never want to do in active-active is if you have 3 cells, you probably only ever want to take one of them out. You never want to go down to 1 cell. So you can set a rule that says that, and ARC will enforce it so that you could never make a mistake. In an active standby, the most common thing is you don't want the standby and the active to be online at the same time taking traffic. And so you can enforce those rules with safety rules. So looking at this situation, this is our active-active. Maybe we've already got NLB-A offline. And perhaps perhaps it only happened a couple of seconds ago, and a new call comes in to say, take NLB-B offline. And that will fail, we guarantee that, in order that you're always safe and you don't have to police that yourself on your side. So this was a pretty quick run through of Application Recovery Controller. At this upcoming reInvent, there are 2 sessions that you might want to have a look into to get a greater level of detail on these. I'd recommend taking a look at them. So this completes our agenda. We've gone through the last sort of 12 to 18 months of releases in Route 53 and Resolver, with DNSSEC, and with Application Recovery Controller. I want to say thank you very much for listening in. We always find it super exciting to talk to customers and understand the cool things that they're building using these products. And so I hope now that you're caught up with these new features, that will stimulate some new thoughts on things to build. Thank you very much.